Look at this landscape. For the communities living in the remote archipelagos of South Sulawesi, climate change isn't a future scenario. It is a daily, immediate reality. Rising tides and shifting weather patterns directly threaten these small, isolated islands. Yet, despite being surrounded by intense sunlight, researchers examined how education was addressing this vulnerability. They found a startling paradox. The students growing up in these environments showed a severe disconnect from their own local ecology. This chart shows the baseline ecological awareness of these students across 4 key areas: consumption, waste management, water conservation, and renewable energy. Renewable energy awareness represents the lowest baseline engagement in the entire dataset. This educational disconnect creates a vulnerability. An entire generation is inheriting a high-risk ecosystem, but they lack the practical knowledge required to maintain their own power systems when the centralized grid fails. The root of this problem lies in the classroom. Standard, centralized science curricula treat physics and ecology as abstract theories, often disconnected from the specific survival needs of island living. To a student here, a solar panel is often presented as a piece of machinery used in distant, wealthy cities, a diagram to be memorized from a textbook, rather than a practical tool they could assemble in their own backyard. Because the science feels so distant, students rarely develop the proactive habits necessary to adapt to their local environmental challenges. Solving the archipelagic energy crisis requires more than just hardware. It requires an approach to science education that accounts for the student's geographic reality. The solution is a pedagogical framework called Ethno-STEAM Project-Based Learning. It is a method that links indigenous knowledge systems, the lived local wisdom of a community, with hard scientific inquiry. Rather than handing out a generic national textbook, researchers used the diagnostic data to prescribe a targeted intervention. Because renewable energy was the area with the greatest deficit, they implemented a curriculum focused on designing and building a mini solar power plant. The core mechanism of ethno-STEM moves students out of the theoretical classroom and into the physical field. They work with their hands, stripping wires and aligning panels under the actual island sun. The student moves from observing standardized facts to actively engineering local solutions. This schematic breaks down the exact physics students apply in the field. The solar panel captures photons, converting sunlight directly into voltage, which travels through a closed-loop circuit. These principles are taught explicitly through the lens of addressing the island's chronic power shortages. By matching the positive and negative terminals and completing the circuit themselves, the abstract math becomes a tangible source of power. By physically building the system, the students see that they can directly manipulate and improve their immediate environment. When that small bulb finally flickers on, powered entirely by a system they built from scratch, the students see the direct result of their engineering. This moment brings renewable energy into the immediate environment, moving it from a textbook concept to a functional part of their own community. Following the intervention, researchers recorded a measurable increase in the students' proactive environmental behaviors and their willingness to engage with local ecological issues. This localized problem-solving represents the type of technical literacy required to maintain basic infrastructure in isolated regions. The Ethno-STEM framework demonstrates that scientific literacy is most effective when it is tied to a student's lived reality. The study demonstrated that aligning scientific inquiry with cultural contexts significantly increases environmental responsibility. What worked in South Sulawesi provides a scalable blueprint for other geographically vulnerable regions facing similar energy challenges. Effective science education must be precisely mapped to the specific ecological needs of a student's geography. These students are graduating with the technical skills to design, build, and sustain